Hello everybody, this is the video for your virtual lab for this week, and it'll be about motion. You'll need a couple of things for this lab, three things exactly. It'll be your toy car, right? And it could be any kind of car, a Matchbox car, a Lego car, it doesn't matter, right? You'll also need a stopwatch or a timer. You can use your phone for this. And then also you'll need some kind of measuring device, like a ruler or a yardstick or a tape measure. Any of those things will work. If you're missing any of these items, feel free to come borrow it from us. I'll let you borrow it. Again, this lab's not due until next Thursday at the end of the day, so you still have time to do this if you need to. So let's go ahead and do this, okay? So the first thing you're going to do in this experiment right now, the first thing you're going to do is you're going to get yourself some level ground, right? So like some flat ground, and you'll put your car in the level ground, right? And if you need help doing this, you can, but what you're going to push your car across the level ground. And when you push the car, you're going to start a timer, okay? And then when the car stops, you're going to stop the timer, okay? On level ground. And you can practice this a couple times. Try to make it so that at least 5 seconds goes by before the car stops, right? And so that way, when you get the data, after the car stops and you got the time, right, what you can do now is use your measuring device like a ruler or something, right, and measure how far your car went, okay? So once you have that information, right, I'm going to explain to you what part A is right now. This is what you're doing in part A. You're going to come down to the first table here, and this is where you're going to record your data, okay? So for when you first start the vehicle, right, before you even start the vehicle, before you start timing, the first one is time 0, and your position is time 0, right? And then it says right here you're going to be measuring the distances in centimeters. So try to make sure you're using a ruler or something that has centimeters to measure how far your car went, right? And then, like I said, you want to try to make it so that your car goes at least 5 seconds before it stops. So practice that, right? And so once you get that done, say you make it go exactly 5 seconds and it stops, you'll fill in 1, 2, 3, 4, 5, right? And then don't worry so much about the stuff in here, but you're going to do the last one, which is at 5 seconds, right? And you'll put how far your car went in 5 seconds, okay? So I'm just going to make a guess here. I'm just going to make up something. Let's say your car went 20 centimeters in 5 seconds, okay? That's good because now you have a total time and a total distance. And what you can do now is do V equals distance divided by time, and that will give you the velocity, how fast your car was going, right? So in this case, it would be the time was 5 seconds, right? So 5 at the bottom, and then 20 for the distance right there. And so 20 divided by 5 is 4. So my theoretical car was going 4 centimeters per second. Okay, so do the same thing with your car. The other thing you need to do too, right, is you need to draw a graph of this data. And it's really easy because on the x-axis you'll put time, and on the y-axis you'll put distance, right, or position. And so for time you'll just put like tick marks 1, 2, 3, 4, 5 for however many seconds you had that you actually measured the car was moving until it stopped, right? And so it's 1, 2, 3, 4, and 5 for 5 seconds, right? You could put in here seconds right there just so you know it's 5 seconds. And then for distance, I would just go to the very top and put a line at the top, right? And then just put the distance that your car was when it stopped. So it was 20 for me, okay? So this distance, of course, is in centimeters, okay? So the reason why we put distance on the y-axis and time on the x-axis is because the distance traveled depends on the time. And so everything that's on the x-axis is called the independent variable, and everything that's on the y-axis is called the dependent variable. So my car's distance it traveled depend on how much time, right? And so I let it go for 5 seconds and it went 20 meters per second, right? So all you have to do now is make the graph, right? So at 5 seconds, I'll put a dot right here at 20 centimeters. And now I can draw a line there, and now I have a nice little graph showing how fast my car was going, right, when I pushed it across some level ground, right? The next part of the experiment, though, is this. You're going to try to do the same thing again, but this time you're going to make it go downhill, right? And so what you're gonna do here is, instead of having flat ground, uh, have some kind of something lift up the car, the track a little bit. So I would use like maybe a book or a pan, like a baking sheet or something flat that's long, or tray, right? And lay it so that the tray is on the ground, right? And then like you have like a book or something that holding it up like that, right? I don't know if you need it to be that high. Maybe make it smaller, make it less high. Okay. Okay. And so you put your car right here at the top. It's a bad car, sorry. Right? There's your car at the top, right? And then this time you're gonna do the same thing again, but this time you don't have to push that hard. You just need to tap it. And as soon as you tap it and it starts moving down the hill, right? As soon as you tap it, start the timer. And when it hits the bottom, stop the timer. Okay? And then do that, and then I'll go ahead and write the data down here. There's another table down here, and this one's for the downhill, right there. So again, you'll be 0 seconds, right, for 0, and position is still 0 because the distance hasn't changed, right? And then whatever time it takes for you here, right, make it the last one, and then fill in the seconds. So try to make it so it takes at least 5 seconds, right, for the car to travel the whole way before it hits the bottom. But if you can't get it to work, it's fine, right? So let's say I wasn't able to get it to work. So this time I'm doing like, I got to go 4 seconds, right? Before it went 4 seconds before it hit the ground. And so I'll fill in the middle part. Oop, I messed up there. 4 seconds, right? So I'll fill in the middle, 1, 2, and 3, right? And then I'll put in the last position, like the distance it went in that 4 seconds when it hit the ground, right? And so let's say that the distance the car traveled downhill. By the way, this distance is actually the distance of the hill going down, right? So this distance right here, not this distance, right? Not this one, right? You want this one right here. The distance of the hill itself, right? The incline, right? And say it went 30 centimeters this time, okay? Right? So now you have that chart again, okay? And so you can still do the graph again, right? Where you have 1, 2, 3, 4 this time. And then your distance traveled up here is going to be 30 now. You can draw the graph again, just like you did before. Okay? So come back up here real quick. And let's say it says predictions. Which car will take longer, right, to reach the bottom or the end, right? Or basically it's like which car goes faster or which car goes slower, right? And so you'll see that when you do this one here, I'm going to predict the one that goes downhill goes faster. Or you can do that too if you want. Downhill. Okay? Will go faster. And so you from this data that you have right here, you can figure out the velocity, right? So it's the velocity equals distance divided by time, right? And so that means that it's going to be 4 centimeters. Oh, no, sorry, not 4 centimeters. It's going to be 30 centimeters, right? Divided by 4 seconds, right? And so what does that equal? I don't actually know, so I'll get a calculator out. 5 divided by 30 is 6. So, or 30 divided by 5 is 6, but what's 4? I'm just going to calculate it just so I don't mess it up for you. That's 7.5. So I get 7.5 centimeters per second, right? So was my prediction correct? Well, if I was going straight, I was only going 4 centimeters per second. But if I was going downhill, gravity helped me out and pushed me, right? And so now I know that I was actually going 7.5 meters per second when I was going downhill. So going downhill actually makes me go faster, right? And so the other one would take longer, right? To go so I'm sorry. So which one takes longer, right? So actually I predicted that the downhill would go faster. So actually what would take longer means that the level one would take longer is what I think, right? And the downhill one would be faster, right? And it turns out that I'm right, okay? Because when I go level, it's only 4 centimeters per second, but when I go downhill, it's at 7.5 centimeters per second, right? So that's basically filling out that top part. So let's look at the results and answer some questions, okay? So it says, look at your graphs. That's the graphs that we're talking about right here, right? This one right here, and this one right here that we just drew, right? For downhill and level. It says, look at your graphs. For the motion with constant speed, right? How do changes in position compared to equal intervals of time? Explain your answer for how speed can be calculated using your data. Well, you just did it, right? You just calculated your data, your speed, by doing the v equals d divided by t. So just put there the formula, v equals distance divided by time. That's the answer to that one. I just wrote it above because we did it, the formula above, to figure out your speeds, okay? Next question. What is the speed of your cart on the level track? You just did this, right? I just did this for you up there, right? So if you want to do it again, remember it's v equals d divided by t. And then I had 20 centimeters was my distance, right? For the level track that my car traveled, and it went for 4 seconds. Or, sorry, it went for 5 seconds before it stopped. So my speed is 4 centimeters per second, right? That's how you answer that one. And then it says down here, next question says, sketch a graph of a position versus time for an object at rest, right? The object does not have to be at position 0. Label your axis. So this is easy, right? If you recall, we go back up here, and when an object is moving, where does the line go? It goes in the upward to the upper right direction, right? It goes like that, right? In that direction. But when the reason why is because as time changes, right, goes up, the distance, right, changes, the position changes and goes up. But if the car is not moving at all, what is the graph going to look like? I'm going to give you a second to think about that. There's a second. If the car is not moving at all, then time still passes, right? 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, and so on, right? But the car's position stays the same, so it's a straight line all the way across. Right? So that's what that looks like. That's that answer. And then it says draw a graph of position versus time for an object that's moving at constant speed. That's easy because that's what you've been doing, right? Time on the x-axis, right? And then position or distance over here, same thing here, right? And that's going to be a straight line. That's how you know, right? If it were not, if it were not constant speed, right? So this is for constant speed right here. Right? If it were not constant speed, it would look like this because not constant speed means it's accelerating, right? For not constant speed, which is also known as accelerating, right? Okay? But remember, though, this question is asking about constant speed. But I just want you to see what it looks like. For not constant speed, right? Or when you're accelerating, the graph would look like this. It starts out slow, right? And then goes up real fast, right? So this right here is not the answer to the question because this is non-constant speed. But constant speed, it's a straight line. Okay, so I already answered these questions earlier, but what is an independent variable for this experiment? It's time. And the reason why it's time is because distance or position, same thing, is the dependent variable. Because your distance or your position depends on how much time passes, right? What are the controlled variables, right? So controlled variables are things that you don't change in the experiment, right? The time changes, right? Your distance changes in the experiment, but the things that don't change are your control variables. So one of the control variables is that you use the same car both times. Right? And then it asks here, was your prediction correct? Meaning which one hit the end first? Mine was correct, yes, because I picked the one that was accelerating due to gravity, right? Because it was going downhill much faster, right? How could these data help you, like these types of graph, help you outside of class? I mean, we do this all the time when we try to find like good gas, right? Cheap gas, right? And so they use those graphs called like miles per gallon, MPG for gas. And that's basically it. That's the end of the lab. So when you're finished with this lab, remember you got to print it out, or if you're using an iPad, you can write all the answers on the iPad. Print it out, or just submit it using your iPad. But if you have to print it out, then scan it. You can use Adobe Scan, or you can just take a picture of it and then submit it to Canvas. And that's it for today's lab. You have any questions, let me know. Send me a Teams message or something, an email. And if you need to borrow any equipment, like a ruler, a car, or uh, a ruler, a car, or a timer, but you can just use your phones, let me know. Okay? Thanks. Have a good weekend, and see you next week.